So you can see over this 5-day period in December, the deaths. Here's the deaths before the intense smog. Here's the deaths after the intense smog. So it really peaked. The smoke peaked, the sulfur dioxide peaked. Okay, so remember what smog is. Smog is smoke plus fog, smog. And actually there's two types of fog, and I kind of looked it up the other day. There's two types of smog. There's the just industrial smog, okay? That's a primary pollutant. And then there is this photochemical smog, okay? Now there's a subtle difference. Photochemical smog actually is a secondary pollutant that takes just regular old pollutants and makes it even nastier. But it has that same kind of haze to it, so photochemical smog. So we talked about ozone being a secondary pollutant the other day. So I think we'll take a look at these little videos. Let you fill in the blanks. So along those lines, there is an index, the air quality index, that people in China, that sort of thing, have access to know on a given day how good or bad their quality of their air is. Not just China, but in the West Coast too. So this is, again, back to London in 1959, and we saw something like this on Monday in Pennsylvania, okay, back kind of the same time period. Of course, we're going to talk at the end of this chapter how there is a cap on emissions now. So this is not what you see anymore. But I thought this was cute. See what you guys think. This one. A topic that was touched on in the video that we watched the other day was this idea that, remember I said if you have sulfur, and actually during combustion it combines with nitrogen, probably just from the air, not from the fossil fuel, but you can create these nitrogen oxides and sulfur oxides that actually then can go ahead and form acids. And so acids within the atmosphere. So acids within the atmosphere then fall down during rain events. But acids in the atmosphere also fall down during snow events. Also, it actually just kind of gives it can fall down as a solid particulate. So that's a bad thing. So one of the things is we have the corrosion. This is actually just, this statue is pitted from acid corrosion. Breathing's an issue. Again, you talked about kind of the long-term effects versus kind of the immediate effects. But I think if you don't have a break from poor quality air, that's where you're going to have a bad deal. So the video we watched on Monday, remember it had that forest that actually was a NASA study that looked at the forest in 53 versus 83, I think, 30 years apart. And they took samples of the forest that was basically de-leafed and of the trees, and they found it was high in acid. So, okay. So, well, just a little bit more about acid. This whole idea of these emissions from burning fossil fuels creating acids in the atmosphere. When they say what the pH is, like for instance, you're probably familiar with the idea that if I would ask most people, they'd say if something is a neutral pH, means it's not acidic, and the opposite of acidic is basic. A lot of times, bless you, people would say pH 7, and you're right. Okay, that means it's not acidic, not basic. pH 7 is what we say neutral. Now, normal water is a pH 5.6. Okay, excuse me, normal rainwater is pH 5.6. This color right here is what our acid rain issue is going on. Now, you might say, well, what's the problem? 5.6 is what normal rainwater is. Well, so what? It's 5.0 to 5.1. Well, that difference of 0.6 or 0.5, it's a logarithmic function, a power of 10, which means that that is a hefty difference in hydrogen ion concentration or acidity. So pH scale is a little bit deceiving. 7's neutral, 5.6 is what normal rain is, and this is kind of what you're seeing here. Okay, now you can almost kind of see the bullseye. The more red it is, the lower the pH. Now this might be a little backwards too. The lower the pH means it's more acidic. That's kind of how the pH scale works. So the video we watched the other day, actually, the guy said something about the pH of acidic or acid rain is approaching, I don't know, we said lemon juice or something. So it's not good. This slide says the reason actually here in our northeast and then kind of on into Canada, we get hit worse is because actually we're under the influence of two reasons. We're under the influence of the mid-latitude westerlies. So basically kind of we get the kind of from upstream kind of comes this way. The other thing is we just have a lot of industry in that region. All right. So this is where in your textbook I think it says something like the solution to pollution, if you want to fix pollution, is dilution. Now your author is not a proponent of that, obviously. We're going to talk about the EPA monitors waste streams, and so like a factory putting out emissions can only put out so many parts per million, that sort of thing. What the factory cannot do is basically take their waste stream and just add water, or if it's a fluid effluent. They can't just dilute it and say we're fine. Okay, so dilution actually is illegal. But Mother Nature actually dilutes pollution just with the wind. And it does it in two different ways. So for instance, this is, they should not have built this city here. What do you think, right? Okay, if this is a prevailing wind, this is a bad thing. Okay, they should have built the city on the upwind side of the factory. So this is with the wind blowing 5 meters per second, and this is with the wind double blowing 10 meters per second. So of course you can kind of see the city gets kind of a breath of fresh air, so as to speak. If you kind of look at how dark it is here, it gives you an indication for the concentration of pollution versus how light it is here. So the increased wind speed does two things. It actually, it takes the waste stream and it takes it twice as fast. So its dwell time, so as to speak, is half as much. So it's less concentrated that way. The other thing is increasing the wind speed actually kind of gives you a little bit of turbulence, so you can take clean air and kind of entrain it into your pollution, your plume. So we talked earlier in this class the idea about a chunk of air that's unstable. Now, if a chunk of air is unstable, it wants to rise. A good example of a chunk of air that wants to rise is because it's warmer than its surroundings, okay? So if a chunk of air wants to rise, that's good for pollution, right? Yeah. So basically you can take polluted air and, again, back to kind of the dilution, it goes up. If a chunk of air is stable, that's not so good, okay? So that basically means that an air does not want to rise, okay? Now, honestly, most air in the troposphere has this gentle ongoing rising, because if you think about the troposphere, we said that it's warmest here and it gets cooler as you go up. So if it's warmest here, we kind of have this gentle ongoing kind of updraft. And I think we talked about kind of hydrostatic equilibrium. But so if it's an example of an atmosphere being stable is basically you have a temperature inversion. We've talked about temperature inversions. So a temperature inversion goes like this. Okay, I'll go ahead and put, this is the troposphere. Let me go ahead and do it this way. This is normal. Okay, this is a temperature inversion. Okay, so normal, actually, we have warm, and it gets cooler as you go up. And so it's buoyant, it wants to rise. That's what we call kind of unstable. That's good for pollution. A temperature inversion basically has a cold chunk of air here where and I have some figures here to kind of show you, but this is kind of your factories down here, okay, putting out pollution. This cold air does not want to rise, okay, it does not want to rise. This is a stable atmosphere, and this is bad for pollution. So how do you get that cold air there? There's a couple ways to do it, and I'm going to kind of talk you through two ways of getting a temperature inversion. One way is we talked, I think, about before, a radiation inversion. We talked about radiation fog. Radiation fog occurs basically as the Earth cools off, and it basically peters off its cooling off. years out, it's cooling off. Basically, a temperature radiation fog is great if you have clear skies, no clouds. Okay, and the other one is a subsidence inversion, and I'll kind of show you what that is. So this is a radiation inversion, radiation temperature inversion. Notice you can see the moon, so your author in this figure is saying, look, clear skies. Okay. Basically what happened is at the Earth's surface, it cooled off over the course of the night and cooled off to the point of getting cold air down here at the Earth's surface. And that cold air doesn't want to rise. And so what happens is basically it kind of acts as a cap on your pollutants. The good thing, I guess, about radiation fog is, or radiation fog or radiation temperature inversion, is when the sun comes off, basically it kind of, if there's no clouds, to go ahead and for the sun to penetrate and heat up your Earth's surface, you can go ahead and fix your temperature inversion. So this sort of pollution actually would be worst, you know, kind of in the morning, that sort of thing, or before the sun comes up. Then this other one, we talked about high pressures, we talked about semi-permanent high pressures. I think your author kind of uses this as an example of something that can happen over our west coast. We got these where the Hadley cell and the Farrell cell bump up against each other and that air is descending. We have these semi-permanent highs. We've been talking a lot about this semi-permanent high, the Bermuda high. And there's a semi-permanent high over here too. So what can happen with the high pressure is basically it can take air and make it, we call it subside, make it go down. And if you can take air and make it go down, what's going to happen is it's going to get warmer, okay? So in this case, basically what we did was we took a normal temperature profile and made warm air here, and we still have colder air here. So that's a subsidence temperature inversion. Okay, so you can kind of see this would be a high pressure up here, making this air go down. And actually, we talked about kind of, you know, the atmosphere is complicated. It's definitely three-dimensionals. And we talked about in order to sustain a high pressure at the Earth's surface, you have to have a column of air moving down. I don't know if you remember that. We talked about cyclone or anti-cyclones like that. So as it comes down, it's squished together and it heats up. And now you have a cool air under warm air. So, oops. Yeah. So this is finally where I say that your author talks about kind of the semi-permanent high over here, especially hitting our west coast. Okay, so here's where I finally get to tell you a little bit of the good news. We looked on Monday at this idea of the Dust Bowl in the 1930s, over-farming, Great Depression, yeah. And actually the Dust Bowl phenomenon, I think, is going to come up if I get my notes together. In the next chapter, when we talk about climate change, there's this thing called positive feedback. Positive doesn't mean it's good, just positive means that it kind of feeds on itself. So after that, I don't have it in my notes, on my slides anyway, but there have definitely been changes in farming, as you might imagine, since that time. But in 1950s, the United States, or states, began putting limits on smoke and particulates that factories could put out. And then in 1970, seems like it should have been maybe before this, but it was in 1970 that the Environmental Protection Act was established. And along with that, then we had emission standards for not only just for particulates and smoke, but also for sulfur dioxide, carbon monoxide, and nitrogen oxides. And also standards for the secondary pollutant, ozone. So that 20 years later, okay, came up with the Clean Air Act. Oh, sorry, the Clean Air Act was amended. It was established in 1970. So this figure table right here is showing you the EPA limits on the different emissions. So we got time. Let's take a look at, let's see what this one is. So we've come a long way since then, I guess is my point. In fact, I've got some slides to kind of show you how far we've come. 1900 to 2010, emissions of sulfur dioxide volatile organic compounds and nitrogen oxides. Notice here about 1970s or so, they interact, you know, our emissions have come down, which is good. That's all good. This actually is looking at from 1990 for a 12-year period starting at 1990, and then for a 22-year period starting at 1990, and then a 12-year period starting at 2000. The negatives are good. The negatives means it's going down that parts per million or percentage, excuse me. So that's all good. So I mentioned that people in China or in San Diego actually have access to there's an app for that. Honestly, there is an app for that. There's an app for air quality index. I was playing around a few years ago and I found the one for China. I really don't care about the one for China. But this is a website that's from your textbook, and this one actually will give you current air quality. So I hope you kind of have a sense for actually the weather, what the conditions of the atmosphere are. Weather-wise, temperature profile can affect the concentration of your pollution. So this is actually up to date as of today. The red would be unhealthy. The orange is above the threshold of 100. So you kind of see there's no hot spots. I'd say today the air is fairly unstable, probably nationwide, which of course makes air quality, improves air quality. So last but not least, and you don't have to necessarily answer this question, but here's a graph, going back 30 years or so. Notice that our emissions have gone down. That's the green line. That's a good thing, right? Our energy consumption has gone up, kind of steadied out. Our CO2 emissions have gone down. Population's gone up, kind of in general. Notice, though, that the orange line says we continue to use our burn fossil fuels to get from point A to point B, and our gross domestic product. The good thing is that the gross domestic product is going up even though our emissions and CO2 are going down. So we can do it. So that's all kind of encouraging. So excellent. Okay, so let's take a look at the homework that's due. I have them here. I don't have a lot to say about them maybe, but we'll take a look. So you're supposed to answer 1, 2, and 4. So 1 goes like this. Talks about ozone. And remember, way back at the beginning of the semester, we talked about good ozone. Where's the good ozone located? Do you guys remember?
It's in the stratosphere.
It is in the stratosphere. So good ozone's in the stratosphere. It's kind of like towards the top, kind of not all the way to the top, the stratosphere, or the ozone layer in the stratosphere. So if that's good ozone, then what do we learn in this chapter about bad ozone? What is ozone? Is it a secondary or primary or secondary pollutant? It's secondary. So my hint is this. My hint is good ozone. O3, of course, is ozone versus, I'll put a slash, bad ozone. And good ozone, you told me it was in the stratosphere. And bad ozone is in the troposphere, closer to home. So kind of write something along those lines. The next one, figure from your textbook, table from your textbook, 13.1, talks about air quality and emissions, but why, can anybody say, why doesn't it list O3 under emissions? O3 is left off. O3 is not there on the emissions table. Anybody?
Is it part of our cars?
Is what?
Is it part of our cars?
No. How do you get ozone in the troposphere? It's a secondary pollutant, exactly. It's not a primary emission. Basically, you take, and volatile organic compounds are one of the things, but it's a secondary pollutant, not there because it needs a reaction. Yep. Because needs to react. Let's see. I say because formed from reaction. How's that? Symbol for reaction is RXN. Because formed from reaction. Then number 4, motor vehicles are a major source of air pollutants. We can use electric cars, but then this goes on to say electric cars produce little or no pollution directly. But on the idea of electric cars, can you see where there could still be an issue with electric cars? What do you think?
Better produce the electricity. So.
That's right. That's what I think too. The electricity has to come from somewhere. I'll put electricity from fossil fuels, question mark. Yep, exactly. And then there's the other 2. Okay, this one, number 5, say you're flying and actually you're going up. So your takeoff, right? So the city has got the whole pollution sort of thing going on, but at one point suddenly you get clear skies. So can you describe why you went from smoggy to clear skies?
Higher in elevation.
Higher in elevation, and what was that kind of sweet point?
Stable.
Temperature inversion. Yep, stable there. Yep. I say you crossed the temperature inversion. The temperature inversion was in place, I guess, and made it all smoggy, and then you went. Okay. Then the last one says, all right, so a good way if you don't want the smog to get your city is basically make your smokestacks taller, which is good because then it won't get you because it's going to be carried away by the wind. Let's see, however, time. It just says explain what happens if you're downwind from that. Yeah. So, yes. Sad faces all around. So awesome. So these will be due on Friday. Oh my gosh.
Is this the bookmark for the final one?
Mm-hmm.